Okay, so as we dive further into polynomial functions, let's talk about analyzing those graphs. And in doing so, we're going to approximate some zeros by graphing polynomial functions and find the extrema of polynomial functions. So here we talk about this location principle. It seems sort of abstract when you look at it. It says y equals f of x represents a polynomial function, and a and b are two real numbers, such that f of a is less than 0 and f of b is greater than 0. Then the function has at least one real 0 between a and b. Whew. Okay, what they're saying is when I have f of a, remember f of x is the same thing as y. So if f of x is y, what they're saying is, this f of a would be the y value. If the y value is less than 0, that means it's negative. Maybe it's negative 3. So right here we have negative 3. And then it says the next value of b is greater than 0, or it would be a positive value. Maybe it's a 2, plus 2. And they're just saying that in order to connect those 2 points, right, I would have had to pass through the x-axis. If my y value is negative and then it goes positive, or if my y value is positive and then it goes negative, at some point in time, I had to cross over the x-axis. And in doing that, I created a 0, or I identified a 0, I identified a solution, a root, all of those things that we call in the x-axis, x-intercepts. But that's what they're saying there, that if we have a change in the y value, the sign of the y, then we have a 0. We've located a 0. So looking at this example, locate of the zeros of the function, determine the consecutive integer values of x between determine the consecutive integer values of x between which each real 0 of f of x equals is located. So this function, and it tells us that we know that this function is x to the 4th. So it could have as many as 4 possible roots. We know that x to the 4th should be met, should probably be some kind of w. But it just depends on how it's been stretched and moved based on its values. But looking here, as my x values change, right, my y value, I have a positive y, a positive y, a positive y, and then a negative y. So right here in between 0 and 1, a y-intercept or an x-intercept occurred. I crossed over there somewhere in between 0 and 1. So then I have a negative, and then a positive. So somewhere between 2 and 3, I crossed back over the x-axis. So that's what they're saying. We can identify those by thinking of understanding of the change in y. When the y changed, we crossed over the x-axis. And it says use the table to sketch the graph. So I know that when I have x is 0, I'm at 1. When x is 1, I'm at negative 1. When x is 2, I'm at negative 3. And then when x is 3, I am stinking way up there somewhere. So I know it's just going to go up that way. So sketching this, it should look like that. And then what else do we know? When x is negative 1, I'm at 3. And then when x is negative 2, I'm way up there at 29. Way up there again. So we'll just do that. I think that's about all we can do, given the sketch, given the information that we have now. We could use technology, and it tells us that. Use technology to check the location of the zeros, input the function into the graphing calculator, and to confirm that. Well, let me do that real quick, and we're going to calculate, put it into the zeros and hit calculate and see what happens. And there we have a quick, plugged it into the calculator, into y1, and I graphed it, and I can see that here's my approximate zeros. Obviously not perfect, but we do have the general shape of what we were looking for. Had we had a couple of more points, we probably could have done and figured out a little bit more of that W, and that it just it's just a matter of how much it's been modified. So thinking of checking these values and understanding how many roots something should have or could have, I did put this over here for you. X to the first is one root, so we cross over the x-axis one time. X to the second, we can have as many as 2. X to the third, we can have as many as 3, and then x to the fourth, 1, 2, 3, 4, we can have as many as 4 possible roots. Doesn't mean we do, just means we can. So there we go. Looking here, if you take a moment to do this equation, you can find out where do my consecutive integers, where do the roots lie here as you put this into the graphing calculator and then sketch the graph. So some of the key things I can see when I go ahead. So when I look at it on the table information, I can see where do my y values change. I can see right here in between -2 and -1, my y values change from a positive to a negative. And then again, between 1 and 2, I went from a negative to a positive. So I know that I have 2 zeros there. I know that according to my slope, or my just understanding of graphs, that constant is going to be my y-intercept. And then, so that's what this graph looks like. I can come over here and see a little bit more when I put it into graph mode. But, you know, basically we should know that we have this, something like that, is what it's going to look like based off those characteristics in the table. So just keep that in mind. So your zeros fall somewhere between x is -2 and x is -1, and then again between x is 1 and 2. Being able to analyze that. Now here, in this identifying the extrema, we have graphed this, we have plugged the points in, understanding that where is my extrema. So this is going to be a relative maximum, this is going to be a relative minimum. There is no maximum or minimum because it continues forever and ever in both the positive and negative directions. And then estimate the x-coordinates at which the relative maxima or the relative minima occur. So looking here, I can see that the minima is a little bit easier. It is at x is -1. So the minimum is near x is -1. The value of x is 1 is less than that surrounding points, indicating a minimum. What they're saying is this is the lowest point, and think about it, we went from a negative slope to a positive slope, or understanding that. And then here at -2, somewhere in between x is -2 and x is -1, we had the maximum occur. It is near x is -2. It appears to be closer to -2 than to -1. And you may estimate, it doesn't say, but we could say possibly, you know, you could say -1.6, because it, you know, it's an estimate, so it just depends what they're asking for and what your options are. You can calculate that using your graphing calculator to come up with the exact minimum and maximums. So here to remember, as we're graphing this and checking this, you can type this into your graphing calculator, input, y input, input the function, hit second, and then graph. So you can see the graph. You can also check out your table, or second and graph gives you your table data, so you'll have that table data. So I would encourage you here to use the table without looking at the image, because we want to be able to interpret the table. So use the table. Okay, so here, these are the values, the input values I got off the table. And just where do my, let's just think, I went from, along my line here, I'm just going to say this is -3 along the x-axis. I went from a -15 to a, at somewhere here is going to be a +7. Then at -1, I went to a 1. Then at 0, I'm at -3. Then at 1, I'm at 1. And then at 2, I'm at -5. This is a fourth degree, it's negative, so I know that it should look like that. And so here I have a x-intercept in between -3 and -2, somewhere there. So something like this. Then I have another one between -1 and 0. And I know that I have this y-intercept, and then I go from negative to a positive, so there's one between 0 and 1. And then in between 1 and 2, I go from positive to negative. Looks something like that. So somewhere the relative maximum occurs, and I drew that graph so I could see it, but I can see that I have a change here. So there is a x-intercept, there is a x-intercept, there is a x-intercept, and there is a x-intercept in between these values, because the signs change. So the relative maxima occurred somewhere between, I'd say about at, occurred near x is -2, right? And then again at x is 1, right there. The relative minima occurred somewhere around x is 0. So looking at that, that's my lowest value point, or relative value. Now here, the total number in this, analyzing this and looking at this chart, let's see, they have the total number of certified pilots in the United States is approximately, can be calculated by this function where x is the number of years since 1930. So this is 1930, this is 1940, 50, 60, 70, and so forth. And the number of pilots in thousands, so it would make sense that as we started flying more, we had more pilots. And then here in the, let's see here, in the 30s, that would make this 1980, 1990, we saw a decrease in pilots, and I can tell you that is probably technology. Saw a decrease in pilots because technology started doing a lot more for us in autopilot, so those kind of things. And they've graphed this function. What are the key features? Looking at the key features, I can see that I have a maximum occurring approximately at 1985. Right, 1985 is somewhere in here, because this is 1930, so this would be 40, 50, 60, 70, 80, and then 90, so somewhere between in between 1980 and 1990. I see a maximum. I also see a relative minimum here occurring somewhere between, let's see, this is 1985, 95, 2005, about 2015. Right, 2015, we started to see an uptick again. So the domain and range of this function is all real numbers, because the function models years after 1990. The relevant domain of the function, though, however, is going to be x is greater than 0, and then f of x is going to be greater than or equal to, I guess, 0, because we're going to start here at this point. It's going to go. Continue to go as we would, according to this, as we continue to get positive infinity, we are going to positive infinity, where the starting point right here, when x is 0, I was at 7.708. And then the extrema, knowing the maxima and minimums, we said that the maximum occurred between 1980 and 1990. The minimum occurred between 2010 and 2020. The end behavior, so that's what they're telling us. The x-intercepts, the intercepts, the y-intercept is going to, so that's what they come up with that. And then there is no x-intercept because it never dips down to a 0 point. And there you go. Symmetry, the graph function does not have symmetry. So that is how we can come up with that information. So you can take a moment here on this function and this next example, and it says the number of quarters produced in the United States can be approximated by this function. It is a third degree function, and it says where x is the number of years since 2005. So this would be 2005. This should be 2007, 9, 11, 13, and 15. And it says use the graph of the function to complete the table and describe its key features. So doing the same thing that we did before, and then identifying its key features. So when I put that into the table and I come up with that data, what information can I get to it? Describe the relative, the domain. Well, we're starting off at 0 for our domain, so we can just say we know that x such that x is greater than or equal to 0. We know that. The relative range now, we are starting at our y-intercept is 3,215. However, if you notice, the lowest y value we have is going to be 428. So it's going to be, greater than or equal to approximately 482, because I put the wrong number in there. My bad. Look on your calculator, not on my paper sometimes. Now the relative minimum occurs somewhere it seems to be that the numbers are decreasing until we hit 482, and then it spikes back up to 853. So in between 2011 and 2013, we have what appears to be a relative minimum occur. And then the y-intercept, we know again where we started when x is 0. And then the graph of the function, it does not have symmetry. If you were to look at it, we can see that none of these numbers seem to be symmetric. No. And then is it blank to assume that the trend will continue indefinitely? Let's see, the production of coins, would it indefinitely? I can't say that we would continue to increase the number of coins, because we're not just going to keep printing and printing and printing, and the number's going to get bigger and bigger and bigger every year. It's going to have a lot to do with how many are in circulation and how many we need. So we can't just assume that we're going to eventually start minting an infinite number of quarters. So I would say no, not reasonable. It is not reasonable to assume it will continue, because there are outside factors to this. Okay, now here I will say when we can create a polynomial function, and this is a little bit more challenging, but the calculator will do most of the work for us. Use the polynomial function and technology to model. The table shows U.S. backpack sales in millions of dollars according to Travel Goods Association. Make a scatter plot, a curve of best fit, and show the trend line over time. Then determine the backpack sales in 2015. Okay, so enter the data into line 1, line 2, into our calculators. This would be line 1, line 2. Choose the scatter plot and hit stat plot. And then what we're going to do is use list 1 as our X list and list 2 as our Y list. And then we can change our viewing window to where it's a little bit better for us. And looking at this graph as we look at our scatter plot, it appears to have this shape, which if we were to extend it out there, looks like a W, which tells us it's probably to the 4th degree. There's some speculation, and we're not always going to be right, but just thinking about it, understanding that the 4th degree polynomial. So now what I can do is, if I know it's to the 4th degree polynomial, the calculator will actually give you its values based on the information that you input into it. So based on your list values, you can go down and you can go down to your regression and go to quartic regression. And we'll do a lot more of this in class. But in doing that, you hit enter, and it will give you think about, this is your A, B, C, D, and E values. So they're telling you that if you wrote that in there and it's saying to round to the nearest tenth, your equation is going to be A is going to be, it says round to the nearest tenth, 0.2, right? Then the next one would be minus 3.9. The next one would be 26.4. The next one would be negative 43.6. And then finally your constant is going to be 1,139, which would round up to 40. And that is what my function is going to look at. Now you can go in and graph that, and you can see it overlays. It would overlay your scatter plot points. And then in 2015, we could look at our table data, and just in 2015, it is going to be 3,523.3. 3,523.3 billions of backpack sales. Let me see here. My graph though was in. It was in millions. It was in millions. So it would be 3.5 billions. So there you go, being able to utilize that information in the graph. And we're going to do a lot of this, and this one could arguably be hard to see that it is a fourth function, but if you saw something that resembled this, I would hope that you can say, hey, that looks like a cubic function, or this, that looks like a quadratic function. So that's the kind of thing we're going to be looking at. Try to make it not too difficult, too challenging, because we're trying to get concept here. We're not trying to trick people. And let's see here, in determining the average rate of change, and of course this check there is the same thing, and we'll do that definitely in class, but just understanding the premise of it. And I guess you are welcome to do it on your own. I will tell you that the answers, though, are going to look something along the lines of, there's your answers if you want to do it on your own and go back and check it and see how it works out for you. Now, finding the average rate of change, again, I said we were going to do this a lot in this class when we started talking about it before, but they're asking for the average rate of change. It says the Ares V rocket was designed to carry as much as 75 tons of supplies and 4 astronauts to the moon and possibly even Mars. The table shows the expected G-force of the rocket over the course of 200-second launch. Find the average rate of change. Sketch the graph and estimate the average rate of change of the acceleration, then check your results algebraically. So we traveled time. They're saying, hey, we went for 20 seconds. This point would be something along the lines of 2.2 and 200 seconds and 2.2, like my ordered pair, right? I got an X and a Y. I put in 200 seconds and I get 2.2 out of it. And then my initial starting point, I started off at 0, and the value at 0 acceleration was about they say 3.4, so we'll just go with 3.4, about 1.34. So there's my 2 ordered pairs that I have. And then so we're examining the average rate of change between here and here. So what does that straight line look like? Okay, so that's what we're calculating using the slope formula. Let's see, and I'm do the math here real quick. This one, throw that in the calculator, and just thinking about that is approximately 0.0045, and then this simplifies to 0.0043, because what did you have? You had, we have what, 2.2 minus 1.34, which is going to be something along the lines of, oh gosh, let's do some math. 6 becomes 11, which would be 8, so 0.86. 0.86 0.86 divided by 200 equals this. So there's your average rate of change. And then interpret the results. So basically from 0 to 200 seconds, the average rate of change of acceleration was increased by this much, 0.043 G's per second. And that's just using that interpretation and trying to think about what's going on, identifying my features, understanding that the average rate of change is simply the slope between 2 points. And now we'll do a little bit more practice, especially with this stuff in class, because it is easy. We just have to let the calculator do the work for us.